Oh, hello and welcome back to our video series. In this video, I will walk you through the setup of your first carotid case based on the meshes that you have created. I have uploaded a template case to Google Drive. This template case already contains a fluent mesh file. You can replace that fluent mesh file with the one that you created once you have played around with this file a bit. So download this template file. Put it in your OpenFOAM case file, which is in my case ASYS TS3 OpenFOAM ASYS3 V912 run. If you are using WSL, you will need to use the shortcut to your Linux home directory that we have created in the last session, and because this file needs to go into the Linux directory and not into the Windows tree. So put that into your Linux OpenFOAM run directory and just save it there. Then we will need a terminal. I'm in my home directory. So the first thing I need to do is I need to initialize OpenFOAM. I initialize OpenFOAM 1912. And then I need to go into the run directory. In this run directory, I will now have my archive file. And I need to unpack this archive file with the command tar, X for extract, V for verbose, tell me what's going on, Z for it's a zip file, and F for use a file as an input, and then the file name. That will unpack the whole thing, and I have now a new directory, Carotid Steady State template in there. If I say want to look into that, I can use the tree command, which will give me an overview of how that directory looks like. So we see the 0 directory, which has all the boundary conditions in. I usually have a 0.original, which is simply a backup of the original 0 drive. So before I do anything, I just copy the 0 drive, the 0 directory into 0.orig. So I can always roll back, and we will see why that is important when we start running this case. Then we have the Carotid Steady State foam file, which is the one file which is an empty file that ParaView will need to be able to open this case later on for visualization. We have the constant directory, which has everything in it that is a constant on that case. That means it has the mesh in it, and we will need to convert that mesh into an OpenFOAM mesh as the first step. It has the transport properties in it. It has RAS and turbulence properties in it, which tell the system what turbulence model we're going to use. In this case, everything is set to laminar, but we do that in these files. And it also has the haemo transport properties in it, which is something that you don't have in standard OpenFOAM, but you have in my version of OpenFOAM, because that has all the blood-specific properties in it, or the particle transport properties, or the blood-specific particle transport geology models. Then we have the system file, system directory, which has the control dictionary in it, control dict, which is the main control file for OpenFOAM. It has a decompose pardict in it, which we will use to decompose the case between different processes, so we can speed up simulation times. It has FW schemes in it, in which we set the discretization schemes for time and spatial discretization for the different terms in our Navier-Stokes equations. And we have the FV solution in this system file, where we set, for example, the convergence criterion. We set the detailed settings for the different solvers. We set which solvers we use, etc. And that is all in the FV solution file. And there's also a surfaces file, which defines a few surfaces which I want to use in post-processing. So that is the case structure here. The first thing we need to do here is to, well, copy this template file, because we don't want to work on that template. You want that template to stay in place for you to be able to use as a baseline for all the other cases. So we could copy this by CP -R, and then what do you want to copy to where? So I could copy Carotid Steady State to Carotid Steady State template to Carotid Steady State, and that will create a new directory. And you see it has created a new directory, which is a copy of this one. I want to delete this though again, because for OpenFOAM cases, there is a better way to do this, and you can even use this on a case that has results in it, etc. So I want to show you that right now. So that is part of the PyFOAM utility system, and it is the PyFOAM clone case command. Don't worry, you don't have to remember all of these. You only need to remember the beginning of that. So PyFOAM CL, and it will tell you what different commands you have, and then clone case.py, because it's a Python command, this one. So it's a Python program that runs that. And then what I need to give it is the case I want to copy, and a name for the case I want to copy it into, and that does that copying. What you see here is not an error message. This is just a warning. It says, okay, the directory does not exist, so it's creating it, which is perfectly fine, which is just what we want. So now the Carotid Steady State directory, and that has exactly the same things in it. So what I want to do first is I want to change into that case. So cd Carotid Steady State changes into that case directory. And in there, I can see all these cases, all these directories that we have discussed here. So the first thing I need to do is I need to convert this fluent mesh into an OpenFOAM mesh. So the first important thing to know is all of the OpenFOAM commands need to be run in the base directory of your case, so which is this one. So don't go into constant and change that fluent mesh. You want to be in the base directory of your case when you run all the OpenFOAM commands. So the command to convert a fluent mesh into an OpenFOAM mesh is fluent mesh to foam. That's easy to remember. You want to convert a fluent mesh to foam, so there's a command that's called fluent mesh to foam. OpenFOAM commands typically start with a lowercase letter and are made up of multiple words. So the beginning of each next word is typically capitalized. So this is fluent mesh to foam, 4 words in one long command name. And then what I need to give that is which mesh file do I want to convert. constant, that's where it is. So it's in here, and then it's fluent mesh. So constant / fluent mesh tells OpenFOAM where to find that fluent mesh, and that is now running, and it takes the fluent mesh and it has created the mesh file in OpenFOAM format, and it has created all these different patches here. Never mind that they created it as wall. We're going to change the boundary conditions later on. So if I say tree now, and now I need to go a bit smaller. So you see the whole tree. So you see this hasn't changed. The constant directory now has a polymesh directory in it, which contains all the different files that make up the OpenFOAM format for the mesh. So the OpenFOAM mesh is not in a file like this one, but it's in a directory. And what we also see, we don't have the 0 orig anymore. So before we do anything with this case, let's just play it safe and copy that 0 file to 0.original. You don't necessarily need that because we can always copy it back from the template directory. But so now we're in the state that I want to be in. We have a mesh file. We have the case defined. We could run this, but before I run this, we'll have a look at how this case will look like. So to do that, I open ParaView. And I point it to my case file. So OpenFOAM 1912 run Carotid Steady State, and I point it to the foam file. It will complain that there is not everything there that it needs, but we will get the mesh loaded and we can have a look at the mesh in there. So let's have a look at how the mesh looks like. So yeah, that is the mesh that we created. So see how the mesh looks like. We also see down here what the different regions are. So apex and sinus here, of the wall into this. So this is the wall surface only. And have a look at the inlet and outlet conditions only. So we have the inlet, common carotid artery, internal and external carotid artery. So the mesh looks fine. So whenever I change anything, I need to apply. So now I have everything loaded. And I leave ParaView open because we can have a look at ParaView while the case is going to run. So what I have here is my editor setup. Your editor will look different. So I recommend, if you run Windows, to use either the Notepad++, which is a very popular editor in Windows. You can also use any editor that you are familiar with. What I find important is that the editor has some kind of tree view on the left-hand side, so we can easily go through all the different files. You get the files opened in the editor window, then you can save that file and easily select the next file where you want to change some settings. So what I find important is that you have a directory tree. So in here, I have my Carotid Steady State. This is an editor that allows me to have projects open. So let me just open this project as a separate, this one file, this one case directory as a separate project. So now that is my case file, or my case directory to be correct. So the first thing I want to look at is the system directory, in which we will find the control dict. And here, this control dict is the main driving file. So this is the main file that controls the. In this file, there are all the settings that control how the simulation is run. All the numerical details are set in the FV themes and FV solution file. So in this file, you will see which application is going to run. This is not necessarily a requirement, but there are some scripts that use this setting to determine which application to start, which code to start. It tells us where the simulation is going to start from. I usually use latest time. You can set first time, that it will start from the beginning all the time, but I usually have it at latest time because then I can easily restart a simulation again, either because it has broken and I had it interrupted and I want to restart it after I made a change, or I just want to continue running it for a while because it isn't quite finished. Then the start time is 0. If there is already a result at, let's say, a later time, then latest time will override this. So I can set start from start time, then it will always start from there. So you can also set start time to whatever 10, then it will always start from the result that has been written 10. But start time and latest time are the two settings here. Stop at end time, which is set here. The first simulation we're going to run is a steady state simulation. The solver still uses the terminology time for that. So the time in a steady state simulation is not a real time. So typically what we do in a steady state simulation is we set the delta time, delta t, to 1, and then the end time will be the number of iterations. Let's assume I want to run 1000 iterations, then I set the end time to 1000. Write control is something I usually set to runtime. You can set it to time step alternatively, and the write interval, if it is set to runtime, will tell the code that in this case every 10 time intervals it will write a result. So if we later do time dependent simulations, and let's say, okay, the time step is a 10,000th of a second, but you only want to run to write out the result every 100th of a second, then you can set 1 times 10 to the minus 4 here and 1 times 10 to the minus 2 here. So I could set that to 1e minus 4 and 1e minus 2 to achieve that. So it would only write out every 100th time step. But later on we will see that we can change time step dynamically, so the runtime setting here makes more sense in many cases. So for this steady state case, I want to write, let's say, every 10th result, so every 10th iteration, so every 10 iterations I want to write a result. Purge write can be interesting. if you want to run a case on, especially for steady state cases, that tells us how many old results it's going to keep. So that will allow you to save disk space, because if you run for a long time, you may want to purge old results to save disk space, because every time it writes a result, it writes all the values for the whole mesh onto disk. So these case files can become massive quite quickly. The write format can be ASCII or binary. Binary is smaller, but I prefer ASCII because that allows more programs to actually work with these results. So please leave that at ASCII. We're going to save space later on. The write precision and the time precision we let as 6. Write compression can be off or on. I leave that as on, which means all the ASCII files, the text files that contain the results later on, they will be zipped with the GNU zip command, and they will have the ending .gz in the end. Many editors and also ParaView read these transparently, so there's no detriment to that. Runtime modifiable true means this file, which the control dict file, whenever that is changed, the code will reread it and use the changed results. So for example, if you are running a simulation and you are observing the simulation and you say, okay, it's not quite finished after 1,000 and you are at 900. So if you're quick enough, you can easily change that to 2,000, save the file quickly, and the code will pick that change up and not stop at 1,000, and it will continue to run. You can also change the time step size while the code is running, and so on. So you can change quite a few settings while the code is running, and the code will pick those changes up. The control dict file is not the only file where you can do this. So many of the control files for OpenFOAM are runtime modifiable, so you can change settings in there. Especially important for some of the more detailed controls of the numerical algorithms. So you can start with a more benign setting, more stable setting, and then switch on the more accurate setting later on, which can be quite useful. So this is the main part of the control dict file that should be in all control dict files, all of these settings. There are more settings, but we'll introduce those when we go for the unsteady state, for the transient simulations, because that's where they are going to be. In the remainder of this, I have identified a few functions. CCA, ICA, and ECA are my surfaces for the inlets and the two outlets. And this function, if you want to run it, takes pressure, velocity, and the hematocrit field and writes it out to a file. So we can post-process only these surfaces, and it will run an average. So it will give you average values for pressure, velocity, and hematocrit. So that is the control dict file. The decompose pardict we're going to need later. This basically sets, okay, one setting that's important here, sets the number of subdomains 4. So this is the file for that. So we will be able to run it on 4 CPUs. If you have more CPUs, change that. The schemes directory is an important one. It sets the numerical schemes that are going to be used. I have set this to second order accurate schemes in this template. The time scheme is an Euler backward scheme. Gradient schemes are Gauss linear as a default, but I set for P, gamma dot, and H, I set them to least squares explicitly. So the least squares are less stable but more accurate. at least in this application. So the default is not actually used in this thoroughly, or in this first simulation. Same here, the default is Gauss linear, which would not work because it would be unstable. We are using a linear upwind, which is a second order upwind setting, and that is basically what you get when you select upwinding in Fluent. Select the second order upwind, and that is that scheme. So I set that for both divergence terms, for velocity and for hematocrit, and for the second order one I use Gauss linear. The Laplacian schemes, Gauss linear corrected, interpolation scheme linear corrected, SN grad scheme corrected, and I will show you where you can find the description to all of these on the OpenFOAM documentation. So these are the defaults, and if I, for example, wanted to set a first order Euler first order scheme, then I would change it here, or if I wanted to run a forward scheme, I could run that with the typical stability penalties. But let's leave this at default for the moment, but this is where you would set, for example, a quick scheme instead of the linear upwind scheme if you want to change these settings. So in Fluent, you would have, in the solver settings, you would have these drop-down menus where you can select the different discretization methods. This is the same thing. The only difference is it doesn't give you a drop-down menu, so it will not allow you to choose one if you don't know that it is there, and you have to choose it with a bit more foresight by looking it up, then changing the value in this text file. But it's basically the same type of system here. So for each of these terms, you can set different discretization methods in Fluent. Many of you will not have looked at that in the past, but when you start doing more sophisticated simulations, it becomes important that you understand what the individual discretization settings are for the different terms in the equations you are modeling. The FV solution file is comes into play once the equations have been discretized. So this comes into play once we have our algebraic system of equations, and the solvers part sets the solvers for the different terms in the for the different variables in our solution term. So for the flux, we use a geometric algebraic multigrid. For P as well, the velocity, hematocrit, and the turbulence properties, which we don't use in this simulation, but it's set here as a default, uses the Gauss-Seidel smooth solver, and there are a few others that are just carried over from another template. So basically all we need is from here to here. We are using the simple algorithm for the steady state simulation, and we're going to use the piezo or the pimple algorithm for the unsteady simulation later on. So I'm going to talk about the simple algorithm in this video only. So what you can set here in principle is the non-orthogonal correctors. The simple algorithm, or we do make mistakes when we don't have perfectly orthogonal mesh cells and the flow is not normal to the surfaces. The non-orthogonal corrector does one correction step each to correct for these errors, which are basically which do come from the projection of the velocity or the flux vector into the local surface coordinate system of the cell, and back into the main coordinate system. So 5 correctors is usual number of these correctors to get a good result on a triangular mesh. And then we have the residual control, where we have a residual setting for the pressure of 1 times 10 to the minus 6, the velocity of 1 times 10 to the minus 7, and hematocrit 1 times 10 to the minus 7 as well. Let's clean this up a bit. We are incompressible, so these 2 settings are not really that important, but we just set a reference pressure, and that is in a particular cell. So if you want your pressures all to be relative to a different location, you can play around with it. But the reference pressure is just a setting that the simple algorithm needs, but it doesn't make a big difference where you set that. So that is the system directory. In the constant directory, we have our mesh, which is in polymesh, which I don't want to go into unless we have problems with the meshing. The most important part is file is transport properties. The transport model that is set in this case is Newtonian. The Newtonian model needs only one setting, and that is the kinematic viscosity nu, which for blood as a Newtonian fluid is around 3.5 times 10 to the minus 6. So it's 3.5 times thicker than water. The density is set here as well, which is not necessary for most OpenFOAM simulations, because OpenFOAM uses kinematic formulations for viscosity and also for pressure. So we will need to look at that when we discuss the pressure settings. So all pressures in OpenFOAM are kinematic pressure, so not in pascals. And the kinematic pressure is the pressure you usually use divided by the density. So if you, for example, set a pressure value of 5 in OpenFOAM for a boundary condition, the actual pressure in pascals will be that 5 times the 1060 that is set here as the density. The haemoFOAM code uses the density to calculate some other properties like the wall shear stress, etc., which I don't want to have kinematic wall shear stresses, but I want the wall shear stress in pascals. So that's why we set the density here. But be careful with the pressure settings. The pressure settings in OpenFOAM are still kinematic. So the viscosity and density setting is done here, and the rest of this file is not used at the moment. These are blocks of settings for the different viscosity models that are implemented in haemoFOAM. So if you choose the Kemada model, for example, then it would not read this viscosity, but it would read these values here. Yeah. The turbulence properties, simulation type laminar means this block isn't red. Yeah? Because if I set simulation type RAS, then this RAS block gets read by the code. But I usually leave it in so I can easily switch turbulence on and off. So I leave the turbulence settings. If you have that, you need this as well. Here I also set the RAS model to laminar, the turbulence to off. So that's 3 locations where we set the turbulence to laminar. So the code should definitely get that hint. So we have a laminar setting here, so you can leave these turbulence property and this RAS properties code file well alone. And the final file in here is the haemo transport properties, which is the file that I need for my code, and that is the file that is read for the transport model. Whenever you run haemoFOAM, you will need this file, even if you don't want to run the transport model. If you don't want to run the transport model, then this one is the one that you need to set. So if we set that to 1, then the transport model gets used and solved, the transport equation for the hematocrit. And then you can set the haemo switch time, because typically we find that the simulation gets a little bit can be a little bit unstable if you switch the hematocrit transport on from the beginning. So typically you would run it without hematocrit transport, so homogeneous hematocrit, and then switch on the hematocrit transport later. So in this case, when I switch it on for steady state, I let run 1000 iterations and then switch hematocrit transport on. But for the first simulation, let's switch the hematocrit transport off, because we're going to use the Newtonian model anyway, and the Newtonian model doesn't use hematocrit. So we just leave the hematocrit as is. haemoFOAM does not allow you to switch the hematocrit off completely, so it will still have a hematocrit field, which we need to initialize, but it won't solve for it. All the other settings are not important at this point, and I will explain those when I explain the transport for hematocrit. So that is the constant directory, and the final directory we need to look at is the 0 directory, where for each of the values in our solution vector, namely pressure, velocity, and hematocrit, we do find one file. So let's have a look at the velocity file first. So this is how a how a foam boundary file looks like. We have a header. So this is something that needs to be in there, so foam knows what's in there. That's true for all the files we have seen, so don't change this foam file header. The rest of the header is simply comment, and you can also see that I did not set this case up the first time in version 1912, but I set it up in a different version of OpenFOAM, but that is only a comment, so that doesn't really matter. This is the important bit, so leave that alone. That tells the code that it's a velocity vector, a volume vector field. So it's on the volume, so it's in the cell, the location where this data is stored, and it's a vector field. It's located in 0, which is the directory here. So that's the location that's in here. And the object is U, capital U, which is the velocity vector as used by the solver. Then we have another line of comment. Then we have the dimension field, which is mass, length, time. So this means meters over second. So these are the powers of the dimension. So the dimension length is to the 1, and the dimension time is to the -1. So that is meters over second. So meters per second is the unit for the velocity we have here. The next one is the internal field, which is the initialization for this. So this means we initialize with a 0 vector, so no velocity initialized. The internal field is initialized with 0. And then we go to the boundary field descriptions. And as you may know from the theory of CFD, boundary conditions in CFD can be basically 2 types. So we can set the value of that property, which would be a fixed value boundary condition here. or we can set the gradient of that value. So we want to look up Dirichlet and von Neumann boundary conditions for those two types of boundary conditions. So here we see that wall, where we know that the velocity is 0, is a fixed value boundary condition with a value of 0. The same is true for the other walls in this, which are the apex, which is our special interest wall region, and the sinus, which is the other special interest region. The outlets, the internal carotid and the external carotid, which are the outlets in our simulation, get 0 gradient conditions. So at that point, we just assume that the velocity doesn't change over the boundary condition too much, which is not perfectly true, as we will see on the results. But if they are far enough away from the areas that are interesting to us, then that is the typical velocity boundary condition. The common carotid, which is the inlet, gets a fixed value boundary condition, and in its easiest form, that is uniform, and 0, 0, 1 is the vector, and that means in x direction I have 0 meters per second, in y direction I have 0 meters per second, and in z direction I have 1 meter per second. I can use this very simple description of this boundary condition in this case because my inlet is oriented normal z axis. So this is normal to the inlet surface. There are more complex and more complicated and more detailed boundary conditions that are useful, especially for inlets. Later, we want to, for example, have a parabolic velocity profile in there because in this case, all the velocity is 1 along the whole, over the whole surface area of the inlet. So also close to the wall, we have a velocity of 1, which will not be a realistic case because we will have a velocity profile. So we will learn other velocity boundary conditions here that allow us to either use a more developed velocity profile like a parabolic profile, or we could use measured data to prescribe at that point. So this is one that we need to change later, but for the first simulation, let's stick with this very simple 1 meter per second in z direction boundary condition. So that's it for the U boundary condition. The P boundary condition looks like this. You see that the dimension of the pressure is not pascals, but it's meters squared over seconds squared, and that is Pascal over kilogram per cubic meter. So that is the pressure in Pascal divided by the density. So that is the kinematic pressure. In the remainder of this field, this fact is not actually important because all the values we have here are 0. So I initialize with a uniform 0. And you see, in this case, I only have one value, which is because this is a volume scalar field. So I have a scalar for pressure, so I only need one value. So I don't need to write this as a vector. So internal field is initialized with 0 at the beginning. Internal carotid and external carotid, which are our outlets, get a fixed value of 0. The wall and the inlet get 0 gradient boundary conditions. And that is a typical setup for many CFD simulations. An inlet will have prescribed velocity and 0 gradient in the pressure. An outlet will have 0 gradient in the velocity and the prescribed pressure. So that is a typical combination here. And a wall will have a prescribed velocity of 0 and a 0 gradient in the pressure, because the static pressure doesn't change normal to the wall. So those are the typical boundary conditions that we have. The boundary conditions for the hematocrit file, just for completeness sake, is at the inlet a fixed value of 0.45. At the internal and external carotid, I use an inlet-outlet boundary condition, and we will discuss that in another session. And the internal field is also initialized with 0.45, which is a typical hematocrit concentration for healthy adults. It's a scalar. It doesn't have a dimension. It's simply a volume fraction. It's simply a fraction. So 0.45 is the volume fraction of hematocrit in this. So that is set here. We need this file even if we don't solve for the hematocrit, because the code wants to read it, because some of the viscosity models need this regardless of whether it's transported and the particles can migrate or not. So this needs to stay in here. So this is the anatomy of the case, and with that I'll end this video, and I'll be back in a short while with how we can run this case now that we have set it up. So one thing that you must not forget with this type of system, you need to write all the data, all the changes that you make to these files. If you have them in the editor, they are not necessarily written to disk immediately. So you want to save all the files. So I want to save hemotransport properties. I want to save this. So, okay, I didn't make any changes in any of the others. So issue a save all on your editor before you go and attempt to run the case. So I'll be back in a while, and we'll have a look at how you can run this case and how this case will look like when you run it, how we can have a quick look at the results, and see you soon.